K-Medoids clustering. Today we'll have an introduction to that. The K-means algorithm is sensitive to outliers because an object with an extreme value will affect the centroid computation and also the clustering. So, to cluster using the partitioning method instead of means or centroid, which is a computed value, we choose an actual object. See, the centroid need not be an actual value because we compute it and it may not match with an actual data point. So this actual object which we wish to use now is we call it a medoid, and this is the alternative to centroid. So K-Medoids algorithm, instead of taking the mean of the object in the cluster as representative, medoids are used. And what is a medoid? It is the most centrally located object in a cluster. So this is the mean. We have 6 data points. We can see the coordinates. It is 1, 1, 1, 2. A very simple small data set. So 6 coordinates and we compute them in the centroid or mean. And this we choose as a medoid. We choose as the medoid. So for these computations of mean or any distance computations, you can go to this link, a previous video link. We'll also give it in the description box. So the K-Medoids algorithm uses the medoids. So briefly, the K-Medoids clustering works in this manner. Initial representatives are chosen arbitrarily. Then we assign data points to the nearest medoid. Then we replace the representative objects with non-representative objects. So this is the iteration part, and continue this process as long as the quality of clustering is improved. And we iterate between these two steps as long as the quality of clustering is improved. And the quality is estimated by the dissimilarity between an object and the representative point. So the distance between object and representative point of its cluster. So the aim is to minimize the sum of the dissimilarity between each object and the representative point. See here, P is the object of cluster Cj and Oj is its representative point. So we compute this for one cluster and sum it up for all the clusters. Now we go through an example where we take two cases. The representatives are chosen arbitrarily. First time we choose D and in the second case we choose C. So the medoid here is 3, 2, 3, 2 and the medoid in the second case is 2, 1. So we compute. Okay, so we need some computation to decide which medoid is better. Which medoid is better? We have two choices here. We could have taken more choices actually. So for this we compute the error as per the given formula in the previous slide. So the error in the first case, error is what? It is the distances of this representative point from all the points. So D, I'll just go through this the 3 how we got it. So this 3 is obtained when we look at D. Coordinates of D are 3, 2 and coordinates of A is 1, 1. So 3, 2 and 1, 1. So we have the first difference 3 minus 1 is 2 and the second difference 2 minus 1 is 1. So that is how we get this 3. And again the rest of the values also we get. We could again refer back to the previous link which I have given for these Manhattan distances we have used here. The Manhattan distance. Okay, all these are given. We could use other distance measures. So Manhattan has been used here. So this we get the error for the first medoid and for the second one we get it as 11. Which means since we want to minimize the error or this function E, so this is a better choice. The first choice of Medoid for these particular set of data points gives us lesser error. So this is more a representative point than C. We'll see in the next video that this choice, this forms the main basis of the working of the K-Medoids algorithm. We will also look into the PAM, partitioning around Medoids, as part of our video lectures. So I hope the concept of Medoids is clear to you. Thank you. Thanks for watching.